Hi, and welcome to this next video on the topic of electricity. If you're serious about your series circuits and particular about your parallel ones, then you've come to the right place. But the next few minutes might be useful also if you'd just like to get a really good grade in your GCSE. So here we go. Starting off, what actually are series and parallel circuits? Well, you might recognize a diagram which looks a little something like this as a series circuit, and it's very simple. We just have our cell at the top and our two bulbs at the bottom. Now the current, as always, comes out of the positive end of the cell like so, down here, through the two bulbs, back up, and then back into the negative end of the cell. Now when you hear the word series, you might think of TV series, as in the episodes in a TV series come one after the other. Well, in a series circuit, it's exactly the same. The components come one after the other, as shown. On to parallel circuits next. Now, as you can see, the circuit components which are used here are identical to those which were used to the left in the series circuits. We have the cell at the top and the two bulbs below, but the wiring of the circuit is very different now. So let's follow the same procedure. We have current which comes out of the positive end of the cell, goes down here like so. When it gets to this point though, something very different happens. Some of the current goes across this path through the top bulb, and the rest of it goes downwards and through the bottom bulb, like so. Both those currents then rejoin at this point and travel back to the negative end of the cell, as shown. So the charges arriving at A have two options in order to get to B. They can either go through the top bulb or through the bottom bulb. Now the paths which they follow have a special name in electricity. They're called branches. So the top path we call branch 1 here, and the bottom path we can call branch 2. Now, just in case it would happen to cause a small problem in your exam, I should also show you this little circuit here. Have a quick look. What do you think of it? Well, hopefully you'll have spotted that this circuit is parallel, because the charges have more than one path which they can follow. But did you also spot that it's completely identical to the circuit above? Let's see how. Now the charges come out of the positive end of the supply here, go down here like so. When they reach this point in the circuit, they again have two paths. The charges can go through the top bulb or the bottom bulb. They'll join together again at this point, and from there they'll travel all the way around the rest of the circuit to the negative terminal of the supply. Now I've got one last thing to show you before we move on. So have a quick look at this circuit here and see what you think of it. As you can see, this circuit has a resistor which is here and two bulbs, one above and one below. But what else do we know about it? In other words, is it series or parallel? Now I know that at first that might seem like a tricky question, so let's follow exactly the same steps that we used just a moment ago. Our current as always comes out of the positive end of the supply, goes down here like so, then through this resistor. Now when it gets to this point, it has two options. Some of the current will go through the top bulb, some will go through the bottom bulb. It will then meet again at this point, and the current will then travel upwards and then left into the negative terminal of the cell as shown. Now this was actually a bit of a trick question, because this circuit has a series section and a parallel section here. A really fancy way of saying that, if you'd like to impress people, is to say that this circuit is composed of a resistor which is in series with two bulbs which are in parallel. Sounds pretty nice, doesn't it? In this next short section of the video, we're going to be looking at how to actually measure current and PD in circuits. In this particular circuit, what we're trying to do is to measure the current through and the PD across the resistor, which you see there. Now you should remember that the device which we use in a circuit to measure current is called an ammeter, and it has this circuit symbol, while the device which we use to measure PD is called a voltmeter, which has this symbol here. The question is, what do we actually do with these two components to allow us to measure current and PD? Believe it or not, but books can and have been written about this very topic. But for your exam, all you need to know is that to measure the current through something, you connect it to an ammeter in series, like this, while to measure the PD across a component, you connect a voltmeter with it in parallel, like so. Now, those words can be a little bit awkward, so when we say that the ammeter has been connected in series, another way of thinking about that is of the ammeter as being connected in line with the component, which is our resistor here. When we say that the voltmeter has been connected in parallel, another way to think of that is to think of the voltmeter as being connected across the component. Next up, we're going to go on to look at how current, PD and resistance actually behave in series and parallel circuits. So starting off with current, the current in a series circuit is the same everywhere. What this means is that we could place an ammeter into any point of this circuit and it would always give exactly the same reading. If the current flowing out of the battery is 2 amps, for example, then the current flowing through both bulbs and all of the wires in the circuit will be 2 amps as well. To explain why this is the case, let's go back to our lovely old river analogy. I knew you kind of missed it anyway. We know that electric current is made up of a flow of charges. If these charges have only one path available to them, then that flow must be the same everywhere. Think about a nice peaceful section of river like this. The flow here is made up of moving water particles. If they all follow the exact same route, then the flow or the current will be the same everywhere. Let's go on next to look at parallel circuits. As you can see, the total current in a parallel circuit is equal to the sum of the currents through each branch. But what does that actually mean? To answer that question, we'll need to take a look at this circuit. As you can see, we're using the exact same components as above. The only difference is that the bulbs are now connected in parallel with one another. If the current through each bulb is 4 amps, then the current going into the parallel section here must be 8 amps. In other words, the total current of 8 amps which was supplied by the cell split up in the parallel section before joining together once more to give 8 amps in the remaining section of the circuit. Now, I know you'd be disappointed if we didn't take one last trip down the river, so here goes. Let's say we go a little further downstream and find an island in the middle of our river here. What might that do to the current, i.e. to the flow of water in our river? Clearly, the total current here must be equal to the total current here, and that total current must split up into 2 for the parallel section like this. Well, the moving charges in an electric circuit behave in exactly the same way. On to PD in series and parallel circuits next, and starting with series. All this statement is saying is that the total PD across the power source in a circuit must be equal to the sum of the PDs across each component. In this circuit, for example, if we're using a 9-volt cell and the PD across the first bulb is 4 volts, then the PD across the second bulb must be 5 volts. Explaining why this is the case is slightly trickier. You're not likely to be asked to do so for your exam, but because it'll help you to understand a circuit like this more fully, which is going to make you even better at solving circuit problems, we're going to have a go right now. The key to this explanation is realizing that the PD across a component tells us how much energy the charges will give to it as they pass through it. A bigger PD means more energy. But how does that explain this circuit? Let's forget about circuits for a moment and think about roller coasters instead. Looks pretty scary, doesn't it? To get from the top to the bottom of our roller coaster, we have to go down 2 hills, this one and this one. As we go down each of these hills, we'll lose GPE. The total amount of GPE we lose from top to bottom will be equal to the amount of GPE we lose going down the first hill plus the amount we lose going down the second hill. In our electric circuit, the energy given to each charge by the cell will be equal to the sum of the energies it gives to both bulbs. That's just another way of saying that the total PD across the cell is equal to the sum of the PDs across each component. Moving on, in a parallel circuit, the total PD across each branch will be the same. So here, if we again use a 9-volt cell, the PD across each bulb will be 9 volts. To explain why this is the case, let's go back to our roller coaster again. In our first roller coaster, We split the descent up into two sections, here and here, but we could have redesigned the track and gotten from the top to the bottom like this. Notice how even though the track has changed, the height is the same and the total amount of GPE lost by the roller coaster car from top to bottom is the same. We actually could have tried a third design and the result would have been exactly the same. In our circuit, when we go from one point to another, the total PD will always be the same. So if we pick these as our 2 points, we can see that the PD across each branch here is equal. Well, we're almost there now with our series and parallel circuit theory. The last thing for us to look at is resistance. It's been a while now since I've given you a new equation to enjoy, so have a look at this one. What do you think it's telling us? Well, it's telling us that in a series circuit, the total resistance is equal to the sum of the resistances of the series components. Here, for example, if the first resistor has a resistance of 3 ohms, the second one has a resistance of 2 ohms, then the total resistance, or total, is just equal to the sum of those, which is 3 plus 2, which gives us 5 ohms. Whoever said that physics was hard? Adding a third resistor to this circuit would have increased the total resistance further. If you're an athlete and you're doing the hurdles, for example, then the more hurdles that are put in front of you, the more difficult it's going to be for you to get to the end. It's the same for the charges in a series circuit. Since each charge will have to go through each resistor one by one, more resistors mean more overall resistance. You'll be glad to hear that you don't need to know the equation for resistors in parallel for your exam, but you do need to know what putting a resistor in parallel does to the overall resistance of a circuit. So have a look at this parallel circuit. So as you can see, we have the cell and 2 resistors in parallel with it. Let's say for the sake of argument here that we're using the same resistors as above. So that is 3 ohms and the bottom one has a resistance of 2 ohms. The question I want you to think about is which of these two circuits has the higher resistance? The top one, the series one, or the bottom one, the parallel one? Now the answer to that question is in fact that the parallel circuit will have the lower resistance. As a matter of fact, the overall resistance of this circuit will be even lower than the resistance of the smallest resistor used in it, which in this case is 2 ohms. When I was doing my GCSEs, this statement made me scratch my head on more than one occasion. How could adding a resistor to a circuit decrease the overall circuit resistance? To answer that, let's go back as always to thinking about the charges flowing through our circuit. If we imagine that this circuit had only the 3 ohm resistor, all the charges would have to go through it. By adding the 2 ohm resistor in parallel with it though, a new pathway is opened up to these charges. In other words, because it has become easier for the charges to get through this section of the circuit, the current through it has increased, which means that its resistance has decreased. Now, I could see that you were starting to wonder there, but don't worry, because we're going to finish off as always with a couple of examples. Okay, example 1, as you can see, is based on a series circuit. The current comes out of the 9-volt cell here, goes through the ammeter, through the thermistor, through the bulb, up through this wire, and back in to the negative end of the supply. Don't let the voltmeter in parallel with the bulb confuse you. This is a series circuit, but remember that if we want to measure the PD across any component, we have to connect our voltmeter across it in parallel. Okay, highlighting the key information given in the question, the PD across the bulb is 3 volts. Part A is looking for the reader on the ammeter. Part B is looking for the PD across the thermistor. And in part C, we need to find out the resistance of the thermistor. So let's get started. First off, let's just note down that the PD across the bulb, in other words this voltmeter reading, is 3 volts. Right, let's start off with the reading on the ammeter. You're probably aware that the right equation to use here is V equals IR. Rearranging, we want to calculate I, so I equals V divided by R, and then subbing in our values, 3 divided by 0.5, which gives 6 amps for the current. Now, it'll make our lives easier if we note down values onto the circuit diagram as we work them out. So I'm just going to label here that the current in this series circuit is 6 amps. A lot of students will lose marks in the exam in a question like this because they use the wrong value for V in their equation. So stop and ask yourself, why did I use 3 volts here and why not 9 volts? To answer that question, we need to think about how to properly read the equation V equals IR. Remember that if V is the potential difference between 2 points in the circuit, like these two for example, then I is the current through that section and R is its resistance. Next, on to part B. To do this one, we have to remember that in a series circuit, the sum of the PDs across each component will be equal to the cell PD. For this circuit, what that means is that the PD across the thermistor, which we can call V, plus 3 is equal to 9. So 3 there, of course, is the PD across the bulb. 9 is the PD across the cell. Therefore, our answer is just 6 volts. 9 take away 3. On now to part C. When we see the word hence in this question, what that means is that we might be able to use one of our previous answers to help us do it. The word otherwise, though, suggests that there might be another way of doing the question. So let's look at both methods here. From part B, we saw that the PD across the thermistor was 6 volts, and we can use this in conjunction with V equals IR to work out its resistance. So rearranging, we have R equals V divided by I, and subbing in our values from the circuit diagram. V is 6 and I is 6 as well, which gives a resistance of 1 ohm. So that's the question done. But what was the second method that I mentioned just a moment ago? The total resistance of the circuit is going to be equal to the PD of the cell divided by the circuit current. Now subbing in my values, that gives 9 divided by 6, which is 1.5 ohms. Now we could get fancy and use the equation for our total, which we saw just a little while ago, or we could just use our common sense. So the total resistance of the thermistor and bulb is 1.5 ohms. The bulb has a resistance of 0.5 ohms, so therefore of course the resistance of the thermistor and our answer must be 1 ohm. On to example 2 now. If you'd like, you can pause the video here and give this question a quick go yourself before going on. Now this is of course a parallel circuit. We know that because the current which comes out of the 3 volt cell here, going down here, has 2 options when it gets to this point. It can either go through the 10 ohm resistor, or it can go downwards and then right through the 5 ohm resistor before going back up to this point. When it gets to there, of course, it goes through the ammeter and back into the negative end of the supply. Part A will hopefully be very straightforward. Because this is a parallel circuit, the PD across each branch will be the same, and so in this case it will be equal to 3 volts, which is the cell PD. Moving on to part B, to calculate the current through the top the 10 ohm resistor, we'll again use V equals IR, which we rearrange to I equals V divided by R, subbing in our values now, 3 divided by 10, which gives 0.3 amps. On to part C, a very similar question, just with a different value for R. So I equals V over R, which is 3 over 5, which is equal to 0.6 amps. To help us answer part D, we can annotate our previous 2 answers onto the diagram. So the current here is 0.3 amps, and here it's 0.6 amps. Thinking back to how current behaves in a parallel circuit, what this means is that the total current entering this point in the circuit must be 0.9 amps. When the 0.3 and 0.6 amp currents rejoin again at this point, the total current will of course again be 0.9 amps. So the reading on the ammeter is 0.9 amps. Well, I've saved the best to last, and part E really is a corker. If the 5 ohm resistor breaks and current can no longer flow through it, then it's more difficult for the charges which arrive here to get to here. In other words, the resistance of the circuit has increased, which will decrease the current, causing the ammeter reading to go down. So that's it. You're done with series and parallel circuits. I know this video was a bit of an epic, but this really is a bread and butter GCSE topic, so hopefully it's one that you find a little bit more appetizing now. Have a go at the exam style questions, and good luck.